Conservation of momentum on this terrific Thursday. This will be a short lesson, and I've said that before, and then I go on talking for about 20 minutes or more. But this is going to be a short one. I'm not going to give you many examples of conservation of momentum. I'll give you one or two maybe. But this is just like conservation of energy, where in a system of objects, once again, a system could be a single object, or it could be multiple objects that you're looking at in working together. So in a system of objects, momentum is conserved. That means all of the initial momentum. So if you looked at all of the initial momentum, and that's a lowercase p, if you added up all of that initial momentum, then it has to equal all of the final momentum in a system or a system of objects. That of course, if there's no net force from the outside acting on that system, if there's no non-conservative forces acting on the system. There can be internal forces in the system itself, and momentum can be conserved, but not from the outside of the system. So you could have friction from the outside slowing things down in the system. So looking at the slide, the very first slide, 6.3, conservation of linear momentum, it literally says pretty much what I just said. If there's no net force acting on a system, then the total momentum cannot change. Therefore, it's conserved. This is the law of conservation of momentum, not energy, but momentum. If there are internal forces, then the individual parts of the system can change, but still momentum is conserved. The total overall momentum has to stay the same. So let me give you an example. I told you I was going to give you an example or two. I'll give you one example and keep this short. I used pool as an example the other day. So initially, what do you do when you initially play pool? Actually real pool on a pool table, or some of y'all have played that little pool game on your phones, I know, and challenge people to a game. But actual pool, you have to hit the cue ball in order to break the other balls. You have to give that cue ball some initial momentum. It has a mass, whatever that is, and you have to give it an initial velocity. So initial momentum would simply be the mass times the initial velocity of the cue ball. Well, what about these other balls down here? Do they have any initial momentum to start with? There you go, 15. There's 15 balls in a rack down here. If you're playing 8-ball, there's 15 balls in a rack down there. So do those balls have any initial momentum? Well, no, they're at rest. So the only momentum initially in this system right here would be what is given to the cue ball. Well, what happens to the cue ball? It comes down here and hits this ball right here with some momentum. So the momentum of the cue ball, some of it is transferred into that ball, and then this ball goes this way, and this one goes this way, and then this one goes this way, and then this one goes that way, and 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 that. I'm just making this up, by the way. I'm just showing you that they go off in different directions. So the balls all go flying all over the table. Well, what happens to the momentum of the cue ball? Well, it slows down, may even come to a stop in some cases, but it slows down. So some of the momentum, or even all the momentum of the cue ball, is transferred into the other balls. So here's the cool thing. If you took the momentum of that cue ball, the cue ball, so we would say the cue ball, and the 1 ball, and the 2 ball, and the 3 ball, and the 4 ball, all the way to the 15 ball, if you took the sum of all those momentum, the sum of all the final momentum of all of those balls, it would have to equal what the cue ball had initially. So this system of objects cannot gain momentum. You can't have these balls, the sum of all of their individual momenta, you can't have it with more momentum final than you gave that cue ball initially. By the way, if you added up all of the y components of each of these balls, the vertical component of each of them. Some of them are going up, some of them are going down. What do you think would happen to those? They would all cancel out because there's only a horizontal component initially. So all of these vertical components would actually cancel, and you would end up with a horizontal component, if you added all the horizontal, equal to that one right there. So that's a lot of math if you had to resolve each of those, and that's why I didn't give you any problems on conservation of momentum, because that would take a lot of work. Bowling would be the same way. I used that example the other day. If you give a bowling ball that has a lot of mass, if you give it a lot of initial velocity, the momentum of the bowling ball is imparted into the pins. And once again, if it has a lot of initial momentum, then the final momentum of the pins are going to have a lot of final momentum. Not more than you started with. But once again, what if you use the thing that little kids use, and it has the little rails on it, and all you did was push a light ball off of there, and it barely makes it down the lane? Then you're not going to get a lot of final momentum. The pins aren't going to go, they're just going to go blah, 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 like I said the other, in that lesson on maybe it was conservation of energy where I talked about that. So it's very similar to the conservation of energy, where energy can neither be created nor destroyed. Well, here we have momentum can't be gained or lost. So that's in a system of objects. Once again, we throw a non-conservative force in there, some outside net force that's non-conservative. Yes, we will lose momentum in this system, which is really what happens in real life. One quick example is, we'll talk about collisions tomorrow. If you drop a ball from a certain height and it bounces back up, the collision occurs when it hits the ground. It loses some energy when it collides with the ground. If it conserved all of its energy, it'd bounce right back up to my hand. So we'll cover collisions tomorrow. There's elastic collisions and there's inelastic collisions. And we'll cover that topic tomorrow. So really, that's pretty much it on conservation of momentum. The next slide, actually 2 slides over, it says collisions can happen so quickly, that this collision happens so quickly that any external forces can be ignored in the collision, and therefore momentum is conserved in a collision like that. So we'll talk about elastic and inelastic tomorrow, where momentum is conserved, but sometimes energy is lost depending on the type of collision it is. So really, that's it for today. There are 2 example videos on Khan Academy that I wanted you to watch. One was two skaters pushing off of each other to show an example of conservation of momentum, and the other one was a ball dropped or something to that extent. Let me see what my website says. Bear with me here while I find it. Staff. Okay, that's wrong. There we are, Brunswick High School. So the 2 videos on Mr. Hall's physics page and the calendar and my daily agenda was watch Khan Academy and watch the bouncing fruit collision, bouncing fruit collision example, and the momentum ice skater throws a ball video. That's what it was. Ice skater throws a ball. That's where I got ball from. So watch those 2 Khan Academy videos. It'll show examples of conservation of momentum. We may have some changes next week coming as far as distance learning goes. I got an email today about that. I will let you know what that involves as soon as that is all ironed out and decided upon. There still will be distance learning going on, but there may be a day set aside for science specifically, and I'll let you know what that looks like as soon as the administrators and teachers get that all decided upon. I'm sure you've heard by now that we will be out at least through Friday, August, where did I get that from? April the 24th, with a tentative start date at Monday, April 27th. So we've now extended the time of distance learning, and so we're going to keep plugging along. We're going to keep doing some physics, and maybe we can do that egg drop project when we get back April 27th, if that's the date indeed that we start school back. So you keep working, and I'll let you know any updates as soon as I hear. I'll let you know if I hear anything before tomorrow. If not, I'll let you know Monday. So keep working and be safe out there and stay home, and we'll talk to you tomorrow.